Good evening everyone, good evening. I welcome you all again to NEET Elite after 1 week, yeah. I hope all of you are doing great, having a good time. So people, you can just let me know in the charts first of all if I'm audible and visible to everyone. Alright, hello Dinesh, hi Chitra, hello Dakshin, hello Khan, hello Bibek, hello Hijaz, hello Mahindra. Hi Fazan, hi Ishpreet, hello Ashwarya, welcome back everyone, welcome back. Welcome back my dear elites, welcome back after so long, yeah? So how are you all doing? Welcome back people, welcome back, right? Okay, I know we are meeting after so long, right? It's been a week, almost, yeah? Perfect, I'm doing wonderful guys, I'm doing great. So, as you all must be knowing, in the last session of General Organic Chemistry, we started something called as inductive effect, right? What we are going to do in the tonight's session, we will be doing something called as resonance. But before moving into the resonance, we'll be doing certain questions based on the inductive effect. Then later on, we'll be moving into the resonance effect as well, okay? Right? So, before starting the session, the ones who are new to the channel, the ones who have just joined in, let me introduce myself. Well people, my name is Wassim and I'm your chemistry master teacher writer on this NEET Elite channel, right? The ones who have not liked the video yet, please do like the video, share the video with friends, do subscribe to the channel and do not forget to hit the bell icon so that you get the notification of every single session which we take live on this NEET Elite channel, right? So do like the video, share the video with friends and do subscribe to the channel as well, okay? Right? Perfecto. So people, you can let me know in the chats if you guys are super duper excited about the tonight's session, right? As I told you, we'll be starting with the questions, with some questions from the inductive effect, then we'll be moving into the resonance effect as well, okay? So you can just let me know in the chats if you people are super duper excited about the tonight's session as well, yeah? Let me see the Josh of the session as I used to see always, right? Perfecto. Yes, Mahindra, you can watch those sessions as well. No issues at all. Perfect, guys. So let's get going. Let's get started with the tonight's session with the first question which is on your screen. Well, people, as per the question is concerned, arrange the following according to their stability, right? We are going to arrange these all on the basis of the stability order. Yes, I hope you remember the inductive effect. Yes, I hope you remember it properly. Right? As we have discussed in the last session, those groups which show plus I effect, they increase the stability of the carbocation. They increase the stability of the carbocation, right? Okay. Yes, those groups which show plus I effect, they increase the stability of the carbocation in general. And those groups which show minus I effect, they decrease the stability of the carbocation, right? They decrease the stability of carbocation. Yes, this is something which we have discussed in the last session as well. I hope you remember it, yeah? Now we will have a look. Over here we have got positive charge on this carbon. Over here we have got positive charge on this carbon. Right here we have got positive charge on this carbon, right? I need to arrange these three on the basis of the stability order, right? I need to arrange them on the basis of their stability, right? Okay. Well, till now we have discussed only inductive effect. So I want you guys to arrange these all on the basis of their stability order on the basis of inductive effect only, right? Well, you can arrange them on the basis of their stability by means of hyperconjugation as well, but that hyperconjugation we have not discussed yet. So I want you guys to arrange them on the basis of their stability by means of just the inductive effect, right? Well, people, if you look at the first one, this is the carbon carrying the positive charge, right? And this is the group which is going to show plus I effect, right? And plus I effect, it increases the stability of the carbocation, right? This group, it will be sending the sigma electrons towards the carbocation, which eventually decreases the positive charge on this carbon, and less the charge on the molecule, more the stability, right? Less the charge on the molecule, more the stability. Yes. Over here in this case, this is the carbon carrying the positive charge. From this side, sigma electrons will be coming. From this side, sigma electrons will be coming. From this side, sigma electrons will be coming, right? Okay. So on all the three sides, sigma electrons are going to come and going to decrease the positive charge present on this carbon, right? So if I compare the positive charge on this carbon and positive charge on this carbon, where is going to be the magnitude of positive charge less among these two carbons? I'll say magnitude of positive charge is going to be less in this carbon, on this carbon, right? Okay, and wherever charge is less, stability is more, right? Similarly, if you talk about this carbon, right, containing the positive charge, on this side, you're going to get sigma electrons, and similarly on this side, you're going to get sigma electrons. On two sides of it, you're going to get sigma electrons. Yes? Now, just compare them on the basis of their stability. I'll say this second one is going to be maximum stable because on all the three sides, you're getting the sigma electrons, which are basically stabilizing this positive charge. So 2 is maximum stable, followed by which one? Followed by third, followed by first, right? This is going to be the order of the stability in the first case. Yes, I'm sure it's clear to everyone, right? Similarly, if you look at the second one, this is CH3, carbon carrying the positive charge, carbon carrying the positive charge. Over here, carbon carrying positive, right? Okay. You have got 3 normal hydrogens attached with this carbon, right? Over here, you have got 2 normal hydrogens and 1 deuterium. Over here, you have got 1 normal hydrogen and 2 deuteriums, and over here, you have got 3 deuteriums, right? As we have discussed in the last session, if you remember, plus I power of tritium is going to be greater than that of deuterium, which is going to be greater than that of protium, right? This is the order of plus I shown by tritium, deuterium, and normal hydrogen. Yes? Now we will have a look. Over here, you have got 3 normal hydrogens attached. Right here, you have got 1 deuterium, 2 deuteriums, 3 deuteriums, right? So wherever you see maximum number of deuteriums, there only this positive charge would have got compensated the maximum. So I'll say magnitude of positive charge on this carbon will be the least, right? Because on the 3 sides of it, you have got 3 deuteriums attached, which are going to send the sigma electrons towards this carbon, and eventually the magnitude of positive charge on this carbon will be least, so its stability is maximum. So this is going to be the stability order. Maximum deuteriums followed by 2 deuteriums, 1 deuterium, no deuterium, right? This is the stability order. Yes, 4, 3, 2, 1, correct? Similarly, if you look at the next case, if I ask you where is the stability of carbocation maximum, see, this carbon is carrying the positive charge, this carbon carrying positive, this carbon carrying positive, right? Okay. Well, this is the carbon which is adjacent to this carbocation, right? And towards this carbon, nitro group is attached, which shows minus I effect, right? Similarly, CN group is attached. It again shows minus I effect. Similarly, fluorine, it again shows minus I effect. And as you must be remembering, in the last session, I gave you the series of the groups, right? Which were arranged on the basis of their increasing minus I power. If you remember, minus I power of nitro group is more than that of minus I power of CN, which is more than that of minus I power of fluorine, right? So this nitro group, right, it is going to attract the sigma electrons towards itself. So the magnitude of positive charge on this carbon will be the maximum among all these 3 carbons, right? So what is the minus I order group of these, what is the minus I order of these groups? Nitro shows the maximum minus I power, followed by CN, followed by fluorine, right? So what is going to be the stability order? See, the magnitude of positive charge on this carbon will be maximum, followed by this carbon, right? So wherever positive charge is minimum, there only stability is maximum, right? So this is going to be the stability order 3, 2, 1. I'm sure it's clear to everyone. You guys can let me know in the chats. Yes? Perfecto. Let's move on to a few more questions. Let's try to solve them as well. See guys, these are a few more questions. Let's try to solve these. Well, arrange the following according to their acidic strength, right? As I told you in the last session, acidic strength of the acid depends on the stability of its conjugate base, right? So in order to compare the acidic strengths of these two, you need to see the stability of their conjugate bases, right? So people, what you guys are going to do, just take H positive out from here. When you take H positive out from here, there'll be negative charge on this oxygen. When you take H positive out from there, there'll be negative charge on this oxygen, right? So you basically got the conjugate bases of these acids, right? After the removal of H positive, you are left with O with a negative charge, removal of H positive, O with a negative charge. So this is basically the conjugate base of the acid, right? Similarly, this is the conjugate base of the acid. Now compare the stability of the conjugate bases. Compare the stability of the conjugate bases. Wherever conjugate base is more stable, there only acid is going to be stronger. We know it, right? Have a look. Over here, fluorine is attached with the second carbon, right? Over here, fluorine is attached with the third carbon, right? And we know inductive effect. It is distance dependent, right? So where do you see, first of all, fluorine, it is going to show minus I power. It's going to show minus I effect. It's going to attract the sigma electron density towards itself, right? Okay. But in the first case, fluorine is attached with the second carbon. In this case, fluorine is attached with the third carbon. So I'll say the effect of minus I shown by this fluorine will be more, right? So this fluorine is going to attract more sigma electron density from here. Yes. So what is going to happen? I'll say negative charge on this oxygen will be less than that of negative charge of this oxygen, right? Okay, because this fluorine is more closer towards the negative charge, right? So eventually it's going to attract the sigma electrons more towards itself, due to which the magnitude of negative charge on this carbon will be the least, and less the charge on the molecule, more the stability. So I'll say conjugate base of the first acid is more stable. And whatever is going to be the stability order of the conjugate bases, same is going to be the order of their acidic strengths, right? So first one is more acidic than that of second one. As simple as that, right? Yes. Similarly, if you look at the next one, you're going to arrange these acids on the basis of their acidic strengths. So what you're going to do, you're going to see the stability of the conjugate base. Now, what is the conjugate base in the first one? Just take this H positive out. Just take this H positive out. There'll be negative charge on this oxygen. So this is the conjugate base. Just take this H positive out, there'll be a negative charge on this oxygen. Take this H positive out, negative charge on this one. Take this H positive out, negative charge on this oxygen, right? Now, we have discussed. If you talk about this carbon, this carbon and this carbon, we have discussed their electronegativity as well, right? Can I say electronegativity of this carbon is maximum among all the carbons which I have pointed over here, right? Yes, because of more angle strain. Yes. That's something which we have discussed in the earlier classes. I hope you remember that, right? So I'll say electronegativity of this carbon is more. If electronegativity of this carbon is more, so this group will be having more tendency to attract the sigma electrons towards itself, right? Due to which the magnitude of negative charge will be the least in the first one, followed by the second one, followed by the third one, followed by the fourth one, right? So wherever the magnitude of charge is least, there only stability is more, right? So stability of the first conjugate base is more, so its acid is going to be stronger compared to all, right? As simple as that. So what is going to be the acidic strength of the following? You'll say this is going to be the order of the acidic strengths, yeah? 1, 2, 3, 4. I'm sure it's clear to everyone. You guys can still let me know in the chats if it is clear to everyone, yeah? Well, I can see majority of the students have given the correct answer. That's wonderful. Perfect. Okay, so let's move on then. Let's try to solve one more question. Okay, we have got few more questions over here on the basis of same inductive effect concept, right? Let's have a look. Let's see how do we solve these sort of questions. People, any species which has got tendency to donate lone pair of electrons, it is called as a Lewis base. Any species which has got tendency to donate a pair of electron is something which we call as Lewis base. And any species which has got the tendency to accept the pair of electron, that is something which we call as Lewis acid. So I want you guys to remember it from now onwards. Lewis base is the one which has got the tendency to what? Which has got the tendency to donate a pair of electron. Right? And Lewis acid is the one which has got the tendency to accept a pair of electron, right? Now, if you look at the first two molecules, I need to arrange them on the basis of their basic strength. I need to see which one is more basic, right? Now have a look. This nitrogen is having a lone pair, right? Even this nitrogen has got the lone pair, right? Now, wherever among these two molecules, nitrogen has got more tendency to donate a pair of electron, that is absolutely going to be more basic, right? So, among which nitrogen? We have got two nitrogens over here, right? Which nitrogen has got more tendency to donate a pair of electron? What do you think? What do you think? Which nitrogen has got more tendency to donate a pair of electron? See guys, if you look at the first one, over here nitrogen is forming 3 sigma bonds. 2 with hydrogen, 1 with carbon. 3 sigma bonds, 1 lone pair, right? Steric number is 4, right? So this is sp3 hybridized nitrogen. This one, 1, 2. 2 sigma bonds, 1 lone pair. 2 plus 1, 3. Steric number 3 means sp2 hybridized, right? Okay. So over here, percentage of S character is going to be 25%. Over here, percentage of S character is going to be 33%. So wherever S character is more, electronegativity is more, because we have discussed electronegativity is directly proportional to percent S character. So electronegativity of this nitrogen is more. If electronegativity of this nitrogen is more, right, will it donate the pair of electron with the same ease as this nitrogen will donate? No way. I'll say this nitrogen has got more tendency to donate the pair of electron, right, as compared to this nitrogen. Because over here nitrogen sp3 hybridized. It has got less electronegativity compared to this nitrogen, right? So which one is more basic? Wherever the tendency to donate a pair of electron will be more, that's absolutely going to be more basic. So first one will be definitely more basic than that of second one, right? As simple as that. Yes. Now if you look at the second question. Over here, nitrogen has got a lone pair, absolutely. Over here, nitrogen will be having a lone pair. We know it. Yes, because nitrogen has got some 5 valence electrons. Out of 5, it has used 3 valence electrons to form 3 sigma bonds. So there'll be 1 lone pair as such on nitrogen. Similarly, there'll be 1 lone pair as such on nitrogen. Now, if you look at this nitrogen, this is sp3. Even this is sp3. So over here, hybridization of nitrogen is same in both the cases. Now, how you are going to arrange them on the basis of their basic strength? See guys, over here you have got chlorine attached. Right here at the same position, you have got fluorine attached. Fluorine has got more tendency, fluorine has got more minus I power in short. So fluorine has got more tendency to attract the sigma electrons towards itself, right? So I'll say availability of this lone pair to get donated is less than that of this lone pair, right? As simple as that. Okay, so which one is going to be more basic? It's simple. You guys are going to let me know the answer. Let me know in the chats first. First one is going to be more basic, right? Because over here you have got chlorine attached, right here you have got fluorine attached. Fluorine shows more minus I power. It has got more tendency to drag the sigma electrons towards itself, due to which this nitrogen is not going to donate its pair of electron with the same ease as that of this nitrogen. Yes, so I'll say this nitrogen will be donating the pair of electron, will be donating the lone pair easily as compared to this one. So the first one is going to be more basic than that of second one, right? As simple as that. Now, if you look at the next one, see this nitrogen is having a lone pair. Even this nitrogen having a lone pair. This nitrogen is having a lone pair. Now arrange them on the basis of their basic strength, right? See, this nitrogen is forming 1 sigma bond and 1 lone pair. 1 sigma bond, 1 lone pair. So steric number 2, this is sp hybridized, right? 1 sigma, 1 lone pair. Sorry, 1 sigma, 1 more sigma with hydrogen and a lone pair. So 2 sigma, 1 lone pair. 2 plus 1, 3, steric number 3, sp2 hybridized, right? So over here, 2 sigma bonds with hydrogen, 1 sigma bond with carbon, right? So 3 sigma bonds, 1 lone pair, steric number 4. So it's going to be sp3 hybridized, right? So percentage S character over here is going to be 50. Over here is going to be 33%. And right here, it's going to be 25%. And we know electronegativity is directly proportional to percentage S character. So wherever S character is least, there only electronegativity is least. So electronegativity of this nitrogen will be least among all the nitrogens. If this nitrogen is least electronegative among all the nitrogens, this nitrogen will be having more tendency to donate this lone pair of electron, right? So this is going to be more basic eventually, yeah? So this is going to be the basic strength, yeah? You can let me know in the chats if every single thing is clear till here, so that I can move on to something called as resonance. Yes? Let me know fast in the chats. Perfect. Wonderful. So let's move on to one more concept. That's something which we call as resonance, right? Have you guys studied resonance before? I'm asking you. You can let me know in the chats. Have you studied? Yes, Umar, I'll be doing one shot on nomenclature as well. Just wait for it, right? Just wait for it. Have you studied this resonance before? Honestly, you can let me know either yes or no. Yeah? Okay, I can see majority of the students are saying no, you have not studied this before. All right, let's get started with the resonance exactly from the scratch. Let's exactly know what this resonance is all about, yeah? First of all, whenever you cannot draw the true structure of the molecule, whenever you cannot draw the true structure of the molecule, or whenever a structure of the molecule cannot explain all the properties of it. I'm giving you two things. First thing, whenever you cannot draw the true structure of the molecule, or a structure of the molecule will be unable to explain all the properties of it, we say that molecule shows resonance, that molecule exhibits resonance. So first point, which I want all of you to take a note of. Whenever a true structure of a molecule cannot be drawn, or a structure will not explain all its properties, we say molecule exhibits resonance, right? Okay, now let's understand it with a common example. Let's understand this statement with a common example, yeah? People, you would have heard about something called as benzene, right? You would have heard about something called as benzene. Absolutely you would have heard, right? Now, if I'll ask you what is the structure of benzene, some of you will say, this is the structure of benzene, right? A few of you will say, this is not the structure of benzene, this is the structure of benzene, right? Some of you will say, this is the structure of benzene. Some of you will say, this is the structure of benzene, right? Okay. But let me tell you, none among them is the true structure, none among them is the actual structure of benzene, right? Why is that? As I told you, whenever a structure of the molecule cannot explain all the properties of it, we say molecule exhibits resonance, right? So this structure or this structure, right? Any of these two structures are not going to explain all the properties of benzene. So I'll say benzene is going to show resonance. Benzene is going to exhibit resonance, right? Let's understand it properly. Have a look. Let me call this as carbon number 1. Let me call this as carbon number 2, for example. Okay? Over here, let me call this as carbon number 1. Let me call this as carbon number 2. Right? In this structure of benzene, between this carbon number 1 and carbon number 2, there is a double bond. And between these two carbons, there is a single bond. Right? And we know strength of double bond is more than that of the single bond. If the strength of double bond is more, that means this bond length, let's call this as C1, C2, let's call this as C3, right? Between C1 and C2 in this structure there is a double bond, and between C2 and C3 in this structure there is a single bond, right? There is a single bond. We know the strength of double bond is more than that of single bond. So if I ask you, will these two bond lengths be same or different? They'll be different, right? I'll say as per this structure is concerned, this is a double bond, this is a single bond, right? So C1, C2 bond length should be less than that of C2, C3 bond length, right? So in benzene, right, you have got two different types of bond lengths, right, due to the presence of double bond, single bond, correct, as per this structure is concerned. Similarly, in this one, there is a single bond between C1 and C2, and there is a double bond between C2 and C3, right? So I'll say C2, C3 bond length will be less than that of C1, C2 bond length, correct, as per this structure is concerned. But when benzene is seen experimentally, when benzene is observed experimentally, all the bond lengths in benzene are identical, right? It is not the case. This is not the actual case. When benzene is observed experimentally, it is seen that benzene has got all the identical bond lengths. All the bond lengths in benzene are identical between all the carbon atoms, right? Okay, but as per this structure, all the bond lengths won't be identical. As per this structure, all the bond lengths won't be identical, right? And as per any of these two structures, right, since due to the presence of double bond, benzene has to behave like the alkene, right? But actually, benzene does not behave like the alkene. So neither of the two structures, right, neither this structure nor this structure, any of these two structures, they are not going to explain all the properties of benzene, right? So I must say benzene is going to show resonance. Benzene is going to exhibit resonance, right? So do remember from now onwards, whenever a true structure of the molecule cannot be drawn, or a single structure of the molecule cannot explain all the properties of it, we say that molecule exhibits resonance. Yes? Now, what this resonance is all about? Before that, you need to understand a few basic points, right? So let me give you those basic points one by one, and I want all of you to take a note of all those basic points one by one, right? Okay, I'm sure it's clear to everyone, right? So neither this structure nor this structure are going to explain the complete properties of benzene. So I'll say benzene is going to exhibit resonance, right? As I told you, for benzene, all the carbon-carbon bond lengths are identical. But as per this structure, that's not the case, right? As per this structure, that's not the case even, correct? Benzene does not behave like the normal alkene, but as per these two structures, benzene has to behave like the normal alkene due to the presence of double bond. But that's not the case actually, right? So it clearly says benzene will be exhibiting resonance, correct? Now, Let's first of all talk about something called as localized electron pair, right? What is localized electron pair all about? Let's understand this localized electron pair. See, I've written a statement over here. When an electron pair is shared between two atoms, when an electron pair is just shared between two atoms, right? We call that electron pair as the localized electron pair. For example, have a look. I've taken two examples right here. See, this is atom A, this is atom B. Right? If I talk about this electron pair in the middle, right? If I talk about this electron pair in the middle, this electron pair is just shared between two atoms. It is shared between two atoms, right? Any electron pair which will be just shared between two atoms, right? I'll be calling that electron pair as the localized electron pair, right? So this electron pair just belongs to these two atoms, right? It is localized. It's localized. It belongs to only two atoms, right? Whenever the electron pair belongs to only two atoms, we call that electron pair as the localized electron pair. Similarly, if you talk about this lone pair of oxygen, this lone pair of oxygen, it belongs to oxygen only. It just belongs to oxygen, right? It does not belong to any other atom. It belongs to oxygen only. So this again the localized electron pair, right? It just belongs to oxygen. When an electron pair is just shared between two atoms, I'll be calling this electron pair as the localized electron pair. Similarly, I'll be calling this lone pair as the localized lone pair, which just belongs to oxygen. Point number one. Now, if this is localized electron pair, then what is delocalized electron pair? Let's understand delocalized electron pair as well, right? Understand the definition. A pair of electron which is shared between more than two atoms. A pair of electron which is shared between more than one atoms. For example, let me take the scenario like this. Let me give the scenario like this. Let's say I've got atom A which is bonded to atom B which is bonded to atom C, right? Let's assume in one scenario, electron pair was found between these two atoms A and B. And in the another scenario, the same electron, for example, was found between B and C, right? In one of the scenarios, the electron pair was found between A and B, for example. And in another scenario, the same electron pair was found between B and C. So, is this electron pair just shared between two atoms or more than two atoms? Absolutely, this electron pair is shared between three atoms basically, more than two atoms. Whenever you'll be having such kind of electron pair, which will be shared between more than two atoms, you'll be calling this electron pair as the delocalized electron pair, right? Yes, as simple as that. So this electron pair, it is not just shared between two atoms, it is shared between more than two atoms. So I'll be calling this electron pair as the delocalized electron pair. I'm sure it's clear to everyone, right? So I'm sure you got two things. One is localized electron pair, one is delocalized electron pair, right? Now the point is, which electron pairs can be delocalized? Do remember, high energy electron pairs, like your pi electrons, they can be delocalized, right? Sigma electrons cannot be delocalized, right? Because sigma electrons are not the high energy electrons. Yes? What is the reason behind that? Why we say pi electrons are high energy electrons? People, we have few days back only, we have discussed chemical bonding, right? In the chemical bonding, I've shown you how sigma bond gets formed and how pi bond gets formed, right? Sigma bond is formed by the axial overlap of atomic orbitals, right? So it is basically a sigma bond. This is the nucleus right here. This is the nucleus of one more atom. This is the sigma bond which gets formed by the head-on overlap, right? And by the axial overlap, by the parallel overlap, which bond gets formed? It is the pi bond which gets formed by the parallel overlap, right? Can I say this sigma electron density, it is under the direct influence of these two nucleus, right? This sigma electron density, there's the sigma electron density in between, right? Basically, this sigma electron density, it is under the direct influence of these two nuclei, right? But if I ask you, this pi electron density, is this pi electron density under the direct influence of nuclei? No, right? Can I say it like this? The force experienced by this sigma electron density is more than that of force experienced by this pi electron density. And the electron density which experiences more force of attraction will be having less energy, right? And that electron density which experiences less force of attraction will be having more energy. So among sigma electron density and pi electron density, which electron density is going to have comparatively more energy? You'll say pi electron density will be having more comparatively energy, right? Why is that? Because the force experienced by the pi electron density is less than that of force experienced by the sigma electron density, right? Okay? So that's why I said the pi electrons, these are the high energy electrons, right? Yes. So first of all, what are delocalized electrons? That pair of electron which is shared between more than two atoms, that's called as delocalized electrons. That's called as delocalized electron pair. Now, which electron pairs are delocalized? Remember, high energy electrons, like your pi electrons, they can be delocalized, right? I'm sure it's clear to everyone. Yes? Now, as we discussed, the high energy electron pair, like pi electrons, can be delocalized, right? And the delocalization of these pi electrons, the delocalization of these high energy electrons, right? That's something which we call as resonance. The delocalization of these high energy electrons is something which we call as resonance. Do let me know in the charts if everything is clear till here, then only I can move ahead, right? The delocalization of these high energy electrons is something which we call as resonance basically, right? Yes? Perfect. And at the same time, can I say due to delocalization, the same electron pair comes under the influence of more than two nuclei, right? The delocalized electron pair, due to the delocalization, the electron pair, the high energy electron pair, it comes under the influence of more than two nuclei, right? So force of attraction on this electron pair will eventually increase. And if the force of attraction is increasing, I'll say energy will get released. And if energy is getting released, I'll say stability is getting increased, right? So due to resonance, due to the delocalization of these high energy electrons, what is happening? Due to the delocalization of these high energy electrons, right? What is happening? Due to resonance, what is happening? I'll say stability is getting increased in the molecule, right? Isn't it simple? I'm sure it's clear to everyone, right? Yes, let's move on. And let's talk about a few more interesting things over here, right? Let's talk about the orbital approach of the resonance, right? Let's talk about the orbital approach of the resonance. Let's understand this resonance a bit more in detail. What is resonance? We discussed till now, resonance is simply the delocalization of these high energy electrons, right? And the delocalization of these high energy electrons is something which we call as resonance, right? Let's try to understand this delocalization of these high energy electrons a bit more in details, right? Let's understand it. Okay, have a look. If you look at the structure of the benzene, which you guys know, right? See, you guys know this structure of benzene, right? All of you? Yeah? Okay. Every carbon atom in the ring, it's a six-membered ring basically. Every carbon atom over here is basically sp2 hybridized, right? Yes? Every carbon atom over here is sp2 hybridized, first of all, yes? Okay. And at the same time, let me tell you, if every carbon atom is sp2 hybridized, that means there will be one unhybridized p orbital. There will be one unhybridized p orbital, right? Which will be perpendicular to the plane containing the sigma bonds, in this six-membered ring. Okay. So basically, let me tell you like this. Let me show it to you like this. Just a second. Let me first of all make the six-membered ring. This is the six-membered ring which you have, right? Okay. Basically, these are carbon atoms. In case of benzene, these carbon atoms are sp2 hybridized, right? The plane containing these sigma bonds, perpendicular to this plane containing the sigma bonds, there will be p orbital present on every carbon. Unhybridized p orbital, there will be p orbital present on every carbon over here. Yes? Right? Now sigma bond has already got formed. Sigma bond, this is the 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 sigma one, this is the sigma one, this is the sigma bond. Sigma bonds have already got formed. Now it is the time for the pi bonds to get formed, right? Understand. How pi bonds are formed? By the parallel overlapping of the orbitals, right? So I'll say, see, if I talk about this six-membered ring, the plane containing these bonds, which I'm representing by red color, the plane containing these bonds, perpendicular to the plane, you have got these p orbitals, which are basically parallel to each other. All these six p orbitals, they are parallel to each other. They're basically parallel to each other, right? Now, if this atomic orbital, if this p orbital and this p orbital, if they are parallel to each other, then there is a possibility that these two atomic orbitals would have got, they would have shown the parallel overlapping. At the same time, these two would have shown the parallel overlapping. At the same time, these two would have shown the parallel overlapping, right? As a result of which, one of the proposed structure of benzene would have been like this. This will be one of the proposed structure of benzene, wherein you have got a double bond between these two carbon atoms, right? A double bond between these two carbon atoms and a double bond between these two carbon atoms. So this is one of the cases, this is one of the probabilities, right? That this can be the structure of benzene. Yes? Right? Now at the same time, there would have been one more probability as well. There would have been one more probability as well. These two orbitals would have also overlapped, right? These two orbitals would have also overlapped, right? These two orbitals would have also overlapped, and due to the sideways overlapping of these orbitals, I can propose one more structure of benzene, right? I can propose one more structure of benzene. So what is that structure going to be? That's going to be what did I do? Just a second. A double bond here, right? A double bond here and a double bond here. This is one of the proposed structure of benzene. This is one more proposed structure of benzene, right? But let me tell you, this is not the actual structure of benzene. This is one of the probable cases that this would have been the structure of benzene if these two p orbitals would have overlapped, if these two p orbitals have overlapped, if these two p orbitals would have overlapped parallelly, right? Similarly, this would have been the structure of benzene when these two atomic orbitals of p would have overlapped. Similarly, these two atomic orbitals, right? So this is not the actual structure of benzene, and at the same time, this is not the actual structure of benzene. So what is the actual structure of benzene? In the actual structure of benzene, let me tell you, all these p orbitals, which are parallel to each other, they simultaneously overlap. In the actual structure of benzene, all these p orbitals, they simultaneously overlap. And they lead to the formation of this angular electron density. Right? Okay? See, if you look at this structure, in this structure, you can exactly say between these two carbons you have got double bond. You can exactly say between these two carbons you have got double bond. Between these two carbons you have got a double bond. So this is the structure containing localized bonding, because you can exactly see between which two carbon atoms there is a double bond. Similarly, in this structure, you can clearly say between these two carbons there is a double bond. Between these two there is a double bond. Between these two there is a double bond. So this structure as well as this structure, they contain localized bonding. They have got localized bonding present in them. They have got localized electron pairs present in them. And those structures of the molecule, which contains the localized bonding, which contains the localized electron pairs, which contains the localized bonding, but cannot explain all the properties of the molecule, those structures are what we call as canonical forms or resonating forms. So this is going to be one of the resonating structure of benzene. This is going to be one more resonating structure of benzene. Either you call them resonating structures or you call them as the canonical forms. So this is going to be one of the canonical form of benzene, and this is going to be one more canonical form of benzene. Right? Yes, but these are not the true structures of benzene. This is the true structure of benzene, wherein you cannot localize your pi electrons. You cannot say the pi electrons are between these two carbons, or you cannot say the pi electrons are between these two carbons. Pi electrons can be between these two carbon atoms. Pi electrons can be between these two, can be between these two, can be between these two. So over here, you have got delocalized bonding present, right? You have got delocalized pair of electrons present. Yes? And how do I represent it? What do I call this first of all? We call this as resonance hybrid. We call this as resonance hybrid, wherein you have got delocalized bonding present, right? Okay, so this is the true structure of benzene basically. How do we make it in 2D? Have a look. How do we make it in 2D? Understand it like this. Understand it in another way as well. Have a look properly. See, this is one of the proposed structure of benzene, right? This is one of the proposed structure of benzene, or I'll be calling this as the canonical form of benzene. And similarly, this is one more canonical form of benzene, right? Wherein double bond is between these two carbon atoms, and these two carbon atoms. These are two canonical forms of benzene which I'm drawing over here, right? Now, in this canonical form, between these two carbon atoms, there is a single bond. But in this canonical form, between the same carbon atoms, you have got a double bond, right? So in the true structure of benzene, there won't be exactly a single bond present between these two atoms, nor will be exactly the double bond present between these two atoms. There will be a partial double bond between these two atoms. Because this structure of benzene, it is saying there should be pi bond, there should be a double bond There should be an exact double bond between these two atoms. This structure says there should be a single bond between these two, between the same carbon atoms, right? So in the actual structure of benzene, there will be a partial double bond between these two atoms, right? Similarly, this structure says between these two carbon atoms, there should be a double bond. But this structure says between these two carbon atoms, there should be a single bond, right? So there'll be a partial double bond between these two carbons, between these two carbons. Everywhere, you'll be having the partial double bonds, right? Right? And this is something wherein you cannot localize the pi electrons exactly. You cannot exactly say wherein you have got pi electrons. Are the pi electrons between these two carbons? Are the pi electrons between these two carbons? You cannot say that. There is the delocalization of pi electrons in this resonance hybrid, right? Wherein in this canonical form and in this canonical form, right, there is the localized bonding. You can clearly say between these two atoms there is a double bond. Between these two atoms there is a single bond, right? You can clearly say from the canonical forms. Okay, but in the resonance hybrid, you cannot clearly say where between which carbon atoms the pi bond exactly lies, right? So over here you have got delocalized bonding, right? Okay, and let me tell you, this resonating hybrid, this resonance hybrid, okay, this resonance hybrid, this is what we call as the true structure of the molecule. This is basically the true structure of the molecule. I'm sure you got the concept of resonance exactly. So let me summarize it quickly. Number one, that structure which contains localized bonding but cannot explain all the properties of the molecule are called as theoretical structures or resonating structures or canonical forms, right? Point number one. Point number two, none of the canonical forms is the true structure of the molecule, is the true structure of benzene. Because I was talking about benzene a few minutes back, right? None of the canonical form is the true structure of benzene. Yes? Right? Because none of the canonical form can explain all the properties of the benzene, right? Okay? And similarly, that structure which contains delocalized bonding but can explain all the properties of the molecule is what we call as resonance hybrid. And the resonance hybrid in benzene I showed you a few minutes back, right? Okay? I'm sure every single thing is clear till here, right? So this is basically the resonance hybrid of benzene. Correct? What is this ring basically? What is this dotted ring? It is that angular density. Right? Which I showed you a few minutes back in the orbital approach of benzene. Right? It is that angular pi electron density. Yes? This is the delocalized pi electron density basically over here. Okay? So resonance hybrid. So do remember, resonance delocalization will be there in the resonance hybrid. But delocalization will not be there in the canonical form. Canonical form contains the localized bonding. It does not contain the delocalized bonding. Delocalized bonding is present in the resonance hybrid. So in the resonance hybrid, delocalization will be there. But in its canonical forms, delocalization won't be there. Right? Yes? I'm sure it is clear to everyone. Right? And this is something which we know. Due to delocalization, partial pi bonds are formed, which we saw exactly. And let's exactly see. Let's compare the bond lengths. If you have got the pure single bond, if you have got the partial double bond, if you have got the pure double bond, right? Where is the bond length more? Definitely bond strength in case of pure double bond is maximum. Bond strength in case of pure double bond is maximum. That means bond length in the pure double bond is going to be minimum, right? Yes? Followed by your partial double bond, followed by your pure single bond, right? I'm sure it's clear to everyone, right? So this is the order of bond strength and this is the order of bond lengths, right? We have discussed this too. Okay. Now if I talk about these high energy electrons, right? These high energy electrons, these pi electrons, right? Pi electrons are actually of two types. One is called as a real pi electron and one is called as differential pi electrons. What are real pi electrons and what are differential pi electrons? See, if you'll be having a double bond or triple bond, you'll be having pi electrons, right? A double bond contains 1 sigma, 1 pi, right? A triple bond contains 1 sigma and 2 pi electron pairs, right? Okay. So basically, the pi electron pairs which are involved in the double bond and triple bond, these are what we call as real pi electrons, right? These are what we call as real pi electrons. And any atom which has got the lone pair, it's called as differential pi. It can be taken as differential pi. Similarly, negative charge with a lone pair. Any atom contains a negative charge with a lone pair, right? That's also called as differential pi electrons. Negative charge with a lone pair, with an unshared pair, right? So basically, your pi electrons, these are two types, real pi and differential pi. Real pi, right? Whenever you'll see double bond or triple bond, right? Whatever pi electron pairs you have got here in double bond or triple bond, these are going to be your real pi, and these are going to be your what? These are going to be your differential pi electrons, right? Let's talk about the energy order of these pi electrons. Negative charge with a lone pair. This electron pair has got maximum energy, followed by a normal lone pair. Then you have got double bond and triple bond, right? So basically, differential pi electrons have got more energy than that of your real pi electrons, in short, right? Okay. Now, talking about the conditions for resonance, I did not show you how to make the resonating structures yet, right? I did not show you that, correct? I did not show you yet. Why delocalization occurs, right? Because due to the delocalization, the electron pairs, they come under the influence of more than two nuclei. So force of attraction on that electron pair will increase. And eventually what will happen? More force of attraction leads to release in the energy, right? Okay, and stability eventually gets increased. So due to delocalization, the delocalized electron pairs, they come under the influence of more force of attraction, right? They experience more force of attraction because they come under the influence of more than two nuclei, right? Due to that, energy gets released and stability gets increased. That is why your resonance hybrid is your resonance hybrid is more stable than that of any of the canonical forms. Because in the resonance hybrid, you have got the delocalization of pi electrons, you have got the delocalization of high energy electrons, right? Okay. Yes. Whereas in your canonical forms, there is no delocalization at all. And wherever there is delocalization, energy gets released. And wherever energy gets released, stability gets increased. As simple as that. Yes. Perfect. So due to delocalization, this is something which I was talking about. Due to delocalization of pi electrons, the pair of electron is subjected to more force of attraction, due to which energy gets released. So potential energy of the system gets decreased, stability gets increased. Therefore, we say resonance increase the stability, right? Therefore, we say resonance increase the stability, right? Now, I was basically talking about the conditions for the resonance, right? What are the conditions which must get followed? So there'll be resonance in the molecule, right? The first condition, there should be the presence of parallel p orbitals which must be coplanar to each other, like we saw in case of benzene, right? Every carbon in benzene had the p orbital which was perpendicular to the plane containing the sigma bonds, right? Yes. So those p orbitals basically were parallel, and at the same time they were coplanar with each other as well, right? So for the resonance to happen, there should be the presence of parallel p orbitals with high energy electrons, right? Which must be coplanar to each other as well. Yes. And this is something which we have understood. The second point. Third point. Resonance hybrid is always more stable because resonance is present in the hybrid. It's not present in the canonical form, right? As I told you. Yes. Resonance is present in the hybrid. Delocalization is present in the hybrid. Delocalization is not present in the canonical form, right? And any molecule which will be having resonance, definitely that will be more stable, right? Yes. Next point. All the canonical forms of a molecule, they must have almost similar energy. It should not be like one of the canonical form will be having maximum energy and then one will be having very, very low energy. No way. All the canonical forms, they must have almost similar energies, right? This is one more condition. Next condition. Out of all the canonical forms, see, I'll be having, after few minutes, you will see, we will be drawing a lot of canonical forms of a molecule, right? And among the canonical forms of the molecule, out of all the canonical forms of the molecule, that structure which is more stable, gives the better representation of the true molecule. So basically, we will be drawing a lot of different canonical structures of a molecule, and among those canonical structures, that structure which is going to be maximum stable, that gives the better representation of a molecule basically, right? So that canonical form which will be more stable, I'll say that will look more alike your hybrid, right? That resonating structure, that canonical form which will be having maximum stability, right? Whose potential energy will be the minimum among all the canonical forms, that will look more alike your resonance hybrid. So that gives the better representation of the true molecule. Yes? Do remember this thing as well. Correct? Okay. All the canonical forms should have same total sum of shared and unshared pair of electrons. What does that mean? See, these are the two structures which I've shown over here. These are the two canonical forms which I've shown over here, right? There is one more condition which must get satisfied. The sum of shared and unshared pair of electrons in all the canonical forms, they must be the same. They must be the same, right? They must be the same. Have a look. Over here there is a single bond. Single bond means there is one electron pair. Over here you have got 3 electron pairs and this is 1 electron pair. 1, 2, 3, 4, 5. So there are total of 5 electron pairs, right? Yes. Basically there is one unshared pair of electron, lone pair, and there are some 1, 2, 3, 4. There are 4 shared pair of electrons. Or in general I'll say there are total 5 electron pairs over here in this canonical form. Similarly in this one, how many are there? 1, 2, 3, 4 and 5. There are again 5 electron pairs. So canonical forms, they must have same shared plus unshared pair of electrons, right? Do remember this thing as well. Yes? Perfect? Right? Yes, we'll be talking about the stability of the different canonical forms as well. Just wait for it. This is just the beginning of the resonance. I'm not going to finish this resonance in the tonight's session only, right? It is going to take one more session, absolutely, right? This is just the basics of resonance which I'm teaching you currently, okay? Now people, wherein do we see resonance? Wherein do we see resonance? For the resonance to happen, there should be conjugation present in the molecule. For the resonance to happen in the molecule, there must be conjugation present, right? And there are lots of conjugations basically which we are going to talk about. Among them, one of the conjugation is going to be pi sigma vacant orbital. Wherever in any molecule you are going to see a scenario like this. For example, this atom A, there is a single sigma bond between B, right? Let's say there's a pi bond. There's a pi bond, right? Then between B and C, there's a sigma bond. And this C has got a vacant orbital as well, for example. This C has got the vacant orbital as well, right? Wherever you see this sort of conjugation, pi sigma vacant orbital, pi sigma vacant orbital, resonance is going to happen in this case. This one is going to show resonance. There are basically a lot of conjugations, right, which we are going to study. Among those conjugations, this is the first type of conjugation. Wherever in a molecule you see pi alternate, pi sigma and vacant orbital, do remember there will be resonance in that molecule. There will be resonance in that molecule. Yes? Okay. For example, I'm going to take certain examples. Let me take certain examples. This is the first example which I'm taking, just to make you understand. See, have a look exactly. This is one of the molecule which I've taken, right? Over here you can see this is the pi, right? This is the pi bond. This is pi. This is sigma. Now we need to see, we got pi, we got alternate sigma as well. Now at the same time, we need to see, is there any vacant orbital in this carbon? Is there any vacant orbital in this carbon? Let me know first. Is there the vacant orbital present in this carbon? What do you think? What do you think? Let me first of all tell you, this carbon is sp2 hybridized, right? This is sp2 hybridized, correct? Now, if I talk about the outermost configuration of carbon, it's going to be 2s2, 2p2. I hope you know this, 2s2, 2p2, correct? This is the outermost configuration of carbon. Now, if I ask you, what is going to be the excited state of the carbon? This is the ground state of carbon. What is going to be the excited state of the carbon? One electron is going to enter here, right? One electron is going to enter here. There's one electron with this, and there are 3 electrons over here, correct? Since there is a positive charge on this carbon as well, what does that mean? That means one of the electron you're going to take out from here, right? So one of the p orbital is empty, right? And this carbon is undergoing sp2 hybridization. This is s and these are p2s, right? These are 2p's. This carbon is undergoing sp2 hybridization. So basically this orbital and these 2 orbitals, they're undergoing hybridization. They're intermixing basically, right? There is one pure p orbital present on this carbon as such, right? Which has not participated in the hybridization. So basically there's a pure p orbital present in this carbon. So over here, do you see pi, sigma and vacant orbital? Absolutely, you're seeing pi, sigma and vacant orbital. So there is a conjugation. And wherever you see the conjugation, definitely that molecule will be showing resonance, right? Now, how do we draw its resonating forms? So first of all, we got to know this molecule will be showing resonance because it has got the conjugation. There is pi, there is sigma, there is a vacant orbital. Now the point is, what is going to be? It's another canonical form. See, this is one of the canonical forms. This is one of the canonical forms of the molecule. This is not the true structure. This is one of the canonical forms. Now from this canonical form, we are going to form more canonical forms. And eventually at the end, we are going to form the resonance hybrid as well, right? Yes, have a look. How you are going to make its more canonical forms. What you guys are going to do, just shift this pi bond over here, right? When you shift this pi bond over here, right, one of the bond of this carbon would have got decreased, and since this carbon's one bond is getting decreased, that atoms whose bond gets decreased, that gets a positive charge. Now there will be a single bond over here, right? There was a double bond, but this double bond I'm shifting over here. So this is going to be your CH, and this is going to be your double bond over here, right? There was the positive charge on this carbon, but now it's getting the pi bond. So this positive charge gets compensated. So it becomes CH2, right? So this was one canonical form. This is one more canonical form, right? Now, if I combine these two canonical forms, I'll be getting what? If I combine these two canonical forms, I'll be getting what? I'll be getting the resonance hybrid, right? I'll be getting the resonance hybrid. How come I'll be getting the resonance hybrid? See, as per this structure between these two carbon atoms, there should be a double bond. As per this structure, there should be a single bond. So in the actual resonance hybrid, there will be a partial double bond between these two carbons, right? Yes, between these two carbons, there will be a partial double bond. Yes. Now, as per this structure, there is a single bond between these two carbon atoms. And as per this structure, there is a double bond. So in the actual hybrid, when you combine it, there will be a partial double bond. There won't be exactly a single bond, there won't be exactly a double bond, so there will be a partial double bond, and then eventually it's going to be CH2 only, right? In the first structure, this carbon carries a positive charge. In this canonical form, this carbon carries a positive charge, right? So in the hybrid, I need to show it. I'll be showing it like this: delta positive on this one, delta positive on this one, right? So this is the true structure, this is the resonating structure. Sorry, this is the resonance hybrid, right? This is the resonance hybrid, okay? This was one of the canonical form, this is one more canonical form, so this is going to be your resonance hybrid. And resonance hybrid contains the delocalization, right? So what I can say, wherever in the molecule you see the delocalization, can I say it's absolutely going to be more stable? Definitely this hybrid is going to be more stable than that of its canonical forms, right? And among these two canonical forms, that canonical form which is going to be more stable, that looks more alike your resonance hybrid, right? Yes? Perfect. Let's take a few more examples. Right? See, this is the true structure of the molecule, yeah, which I showed you. Now, let me take one more example over here. Have a look properly what we are going to talk about. See, guys. First of all, will there be resonance in this molecule? Let's check that. Since we are only talking about only one type of conjugation right now, that is your pi, sigma, and vacant orbital. Let's exactly see in this molecule, do we see the pi, sigma, and vacant orbital or not? If there was the pi, sigma, vacant orbital, definitely it's going to show the resonance, right? And if it is showing resonance, we are going to form all the resonating forms. We are going to form all its resonating structures. Let's have a look exactly. See, guys. First of all, you can see there's a pi bond over here. There is alternate sigma as well. Now let's see, will this carbon have the vacant p orbital over here or not? Absolutely it's going to have, because it's CH2, it's sp2 hybridized, right? And few minutes back only we saw CH2 positive, right? It is absolutely going to have the vacant orbital. Few minutes back only we saw, right? So pi, sigma, vacant orbital. So is it going to show resonance? Absolutely it's going to show resonance. So now how the shifting of electrons will take place. Have a look. Now shift this pi bond over here, right? When you shift this pi bond over here, towards this carbon, one bond gets decreased, and that carbon whose bond gets decreased, that is going to get positive charge, right? So let me make it like this for you. So basically, I've done nothing with this one, I just shifted this pi bond over here, right? Due to which this carbon gets the positive charge now, right? Earlier there was a single bond, now there'll be a double bond, right? Yes, earlier there was a positive charge on this carbon, now due to this double bond, right, there won't be any positive charge. That positive charge would have got compensated, right? Yes, so this is one of the canonical forms. Now, do you see the conjugation again in this? I can say yes. I can see conjugation in this. I can see again pi, sigma, vacant orbital. See, this is basically your pi, this is sigma, and this is basically CH2 positive. There are two hydrogens attached with this one as well, right? Okay, sorry, there is one hydrogen attached with this, okay? Now, you have got again pi, this is sigma, this vacant orbital. pi sigma vacant orbital. Again, there is a conjugation. Again, you'll shift this pi electron pair over here, right? You'll shift this pi electron pair over here. That means positive charge will come on this carbon. So what is going to be your one more canonical form? Let me make it for you. Have a look. This is going to be a pi bond now, right? This carbon was having the positive charge. Now this positive charge would have got compensated with this pi bond, right? Now this carbon gets the positive charge. There is a pi bond over here. This is a double bond and this is CH2, right? Now do you see conjugation again? Yes, I can see the conjugation again. This is pi, this is sigma, this is a positive charge. So shift this, keep on doing that. Let's see what is going to happen at the end. So now there'll be a pi bond over here. The positive charge on this carbon would have got compensated. Now there comes the positive charge on this carbon, right? There was already a double bond over here. So this is a double bond CH2, right? Now, do you see the conjugation again? Yes, I can see the conjugation. This is pi, this is sigma, this is vacant orbital, right? So shift it again. So what is going to be my next canonical form? Have a look. Guys. There'll be a double bond over here, there'll be a double bond over here, there'll be a double bond over here. Earlier, this carbon was having the positive charge, now it's getting a double bond, so positive charge would have got compensated. Now this carbon is going to get the positive charge, and there'll be a single bond over here. This is CH2 with a positive charge. Now if I ask you, is this canonical form and this one, I mean, are they two different canonical forms or same canonical forms? What do you think? I mean, are these two the canonical forms? What do you think? Absolutely, these are the two canonical forms. First one and the last one, these are two canonical forms. But let me tell you, they have got same energy, they have got same stability, right? As you can see, they look identical, correct? Right? They are two different canonical forms, but their stability is different, but their potential energy is different, right? Yes, they look similar. Okay? So these are all the canonical forms of this molecule which I had taken in the beginning, right? So if I want you guys to make the resonance hybrid of it, will you make it? See, this structure says between these two carbons there is a single bond. As per this structure, there is a double bond. So between these two carbons, if I combine all the information given by all the structures, right, between these two carbons, there should be a partial double bond, right? See, this structure says there should be a double bond between these two carbons, but this structure says there should be a single bond. So between these two carbons, there should be a partial double bond, right? So what is going to be my resonance hybrid? See what is going to be my resonance hybrid. Right? In one of the structure, this carbon is getting the positive charge. In this structure, this carbon is getting the positive charge. In this structure, this carbon is getting the positive charge, delta positive. In this structure, this one is getting the positive charge, correct? So this is going to be basically my resonance hybrid, whose stability is going to be the maximum among all. Till now, I did not discuss the stability of these resonating structures. Stability of resonating structures I'll be discussing in the next session, not in the tonight's session. Yeah, I'm sure every single thing is clear till here, right? So these are all the resonating structures of this molecule which we have already drawn, and this is the resonating hybrid, resonance hybrid, correct? Similarly, you can take this case, right? You can make its resonating structures on your own. So first of all, this is pi, this is sigma, there's a vacant orbital with this carbon, right? You can check it out too, right? So definitely resonance is going to happen, right? Shift this electron pair over here. So what is going to be its one more resonating form? It's going to be a double bond over here, right? And this carbon is going to get the positive charge now because the one of the bond of this carbon gets reduced, right? Now do you see conjugation again? This is pi, this is sigma, this positive charge. Again, something's going to happen. Shift this electron pair, shift this pi bond over here. So what is going to happen? So this is going to get the double bond, right? This carbon was having the positive charge. Now due to double bond, the positive charge would have got compensated. And now this is going to get the positive charge, right? Okay. So can I say this one and this one, are they going to be same or different? What do you think? Are they going to be same or different, my dear people? Let me know fast. Let me know fast. The first one and the third one, are these same or different? Are these same or different? These are different basically, right? Is that? Is that? So I'm proposing this question to you. You are going to let me the answer of this question in the comment section, right? So basically, due to resonance, what is happening? Okay, first of all, if I want to make the resonance hybrid over here, what is going to be my resonance hybrid? What is going to be my resonance hybrid? This is going to be your resonance hybrid. So this carbon gets delta positive, this carbon gets delta positive, and this carbon also gets delta positive, right? This is my resonance hybrid, correct? Which is absolutely going to be more stable than all its canonical forms, right? Okay, and due to the distribution, so basically if you can understand one more thing, see, in this structure there is positive charge on this carbon, in the other structure positive on this one, in the other structure positive charge on this one. Can I say due to resonance, positive charge is getting distributed, charge is getting distributed. If charge is getting distributed, can I say the volume charge density gets reduced, gets decreased, and lesser the volume charge density, more the stability. We have discussed that too. Volume charge density is inversely proportional to stability due to the distribution of charges, right? Okay, due to distribution of this charge, what is happening? The charge density is decreasing, and due to decrease in charge density, stability is increasing. As simple as that, right? Okay, I'm sure it's clear. Okay, if I ask you, will this molecule show resonance? This is the last one which I'm going to talk about right now. After that, I'll end the session. Rest of the things we'll be discussing in the next session, right? Just let me know, will this molecule show resonance? I'm leaving it up to you. Let me know in the chats first. Will this molecule show resonance? What do you think? Waiting for your answers in the chats. Yeah? Is that? Is that? Is this molecule going to show resonance? So I can say there's a pi bond, there's a sigma bond, and there's a positive charge, right? So there's a conjugation. Pi sigma vacant orbital, pi sigma vacant orbital, there's a conjugation. So resonance should happen. So this bond you're going to shift over here. So what eventually you're going to get, this is your R, this is C, there is a single bond, and this oxygen will be getting the positive charge, and there's a double bond, and this is CH2, right? So as per you guys, this should be the canonical form of it, right? But no way. Why is that? Because what is happening, if resonance takes place over here, oxygen is getting the positive charge. Positive charge on the electronegative element makes it highly unstable. Positive charge on an electronegative element makes it highly unstable. Highly unstable means more energy. So I told you a few minutes back, in the conditions of resonance, I told you all the canonical forms, they must have similar energies. So will the two have similar energies? No way. This one will be having more energy than that of this one, right? So is this one going to be its resonating form? No way. This is not going to be the resonating form. Yes, because positive charge is coming on oxygen, which makes it highly unstable, which increases its energy a lot, right? So this molecule, if you cannot draw its canonical form, that means it's not going to show resonance, right? As simple as that. Yeah? Okay? Alright, so talking about these two, let's talk about these two in the next session. The next session will be starting from this point. From this point, we are going to start the next session, right? Because till now, it's already 10:10. Okay, so I've got one more session coming up on Vedantu JEE English channel, right? So let me end it here. From this point, we are going to talk in the next session. I'm sure you would have got the concept of resonance properly. The ones who have not liked the video, please do like the video, share the video with your friends, and do not forget to subscribe to the channel. And at the same time, let's meet up at 10:30 tonight on Vedantu JEE English channel, in which I'll be discussing all the previous equations from the chapter Chemical Equilibrium, right? So do join Vedantu JEE English channel at 10:30 tonight, in which I'll be doing some great questions from the chapter Chemical Equilibrium, which have been asked till now in your different competitive examinations, right? Okay, and do let me know in the comment section if you liked the lecture or not. So with this, I'm going to take a leave. I'll see you guys tonight at 10:30. Till then, you guys take care. Bye-bye. God bless you all and love you all. Take care, guys. Bye-bye.